I think we should start. Okay. Well, good morning, everyone. Thank you for joining the second webinar of Back to Fuel project. My name is Ignacio, and I work at NanoGap. NanoGap is responsible for dissemination and exploitation of the project, of the European project. And today, an hour ago, we had the pleasure to have a interesting conversation about how modeling the atomic quantum clusters and how the shape could affect the final product and the environment at the end. And now Professor Arturo López Quintela will give a talk in depth about what atomic quantum clusters are. But before I start with Professor, I would like just to summarize a little bit the Back to Fuel project. For all of you that has enjoyed the previous webinar, okay, Back to Fuel is the acronym of bacterial conversion of CO2 and renewable hydrogen into biofuels. Okay, our aim is to demonstrate at TRL5 the possibility to produce biofuels from CO2, water, and sunlight using different microorganisms that has modified by CRISPR-Cas. And by two different methodologies, biochemical processes, we are gonna be able to produce more butanol, more ethanol that will be used in the transport sector, okay? So at the end, we couple two methodologies: photocatalytic process using the atomic quantum clusters, the catalyst, and the energy from the sunlight, plus the water. We are able to transform, to split the water into hydrogen and oxygen. Then this hydrogen will feed the bacteria in a second step. That will be fed by CO2 as well, and produced by a biochemical process reaction, biofuels. Okay, this bacteria, as I said before, is modified by his genes are modified to be more selective to one product. So we couple nanotechnology, biotechnology, chemical engineering, because we are able to couple, to join both technologies, and at the end, economy, because economy is also important. We want to stop at TRL5. We want to reach higher TRL at TRL9 in the shorter time. So that's the reason we have organized 6 webinars. Each one of them according to the discipline I have already explained. And well, as I said before, this is the consortium. Most of them are working together, are responsible for the whole project, but USC, NanoGap, and Lancaster are more related to IQCs, modeling, synthesis, characterization of IQCs. Wageningen is more related to genome editing. And Vito is responsible for the biochemical system reaction design, the reactor, and so on. And Berlin is the responsible for the photo production of hydrogen, and they're responsible for coupling and demonstrate this technology, okay? And as I said, now we have the pleasure to have with us Professor Arturo López Quintela, that will explain in more detail what are AQCs. And well, thank you, Arturo, the floor is yours.
Okay, thank you, Ignacio, for this nice introduction. I will share now the screen. Let me see. I hope you can see that. Oh, sorry.
Yes, we can.
Yeah.
Mm-hmm.
Let me see here. I have here in the screen, my screen. I have something. Okay. Okay. So I will explain this brief talk. What are subnanometric clusters, and I will try to see that they are exciting materials at the transition between nanoparticles and atoms. Yeah, and I'm the Nanomag laboratory at the University of Santiago de Compostela. I will take probably better the laser point to that. Okay, let's go to the next slide. So you know that when you're working in nanoparticles, there are scaling laws of different properties that, due to increasing surface volume of the particles, the properties can change with the diameter, with the size of the materials. And this was very good in many areas, like in catalysis, because just by reducing the size, you can increase the activity of the materials. Yeah. But we want to go to, beyond the nano, and this is in this area. Below approximately 1 to 2 nanometers, in which the dimensions of the system becomes similar to some wavelengths, like the Fermi wavelength or the de Broglie wavelength. In this area, there is a breaking of the scaling law, so you cannot extrapolate from the size directly to the properties of clusters. So the properties should be different. Yeah. And you can see here, for example, for a metallic nanoparticle, when you reduce the size, so this follows the scaling behavior, but when you arrive an area around a size of around 2 nanometers in size, so the metallic behavior disappears. And you enter into this area in which the amount of atoms in the particle are below 150 atoms, or around below 1.5, approximately 1.5 nanometer. In this, the particles do not have anymore this metallic behavior, then have less tonic, let's say less tonic behavior. Yeah. And in particular, we are focused on the smallest size of this area. So we're working usually with clusters below, let's say, 20-25 atoms. Yeah. So from 2 to around 20 atoms. Yeah. I will explain in this talk why we are working in this area. So the properties change, and why? This is very simple. You just have an electron in a box, and you reduce the box and the levels due to this quantum confinement. The difference between the levels is increases. Yeah. And you enter into the area of clusters, in which by changing the size, and this is particularly important for sizes below 1 nanometer, then the difference between the orbital, the high occupied molecular orbital and low unoccupied molecular orbital, this is much larger than gate area. And in this range of sizes, just by changing one atom to in the cluster, then this change dramatically the homolume gap, and then change the properties. Yeah. So this is just by a picture in which, for example, by changing from a silver 3 atom to a silver 6, this very simple approximation of the Gillian model, in which we only characterize by this position of the homolume. And you can see that by changing the sizes of the cluster, by changing the metal, you can approximately span the behaviors into all different behaviors that the semiconductor has. Yeah, But okay, you can do that, but by changing in very small scale the size of the atoms. So this is a new possibility to make bandgap engineering with metal cluster. So the thing is that can be these naked clusters synthesized with the same wet chemical method that are using for preparing nanoparticles, and the reason is yes, and I can explain to you how this can be done. Yeah. So the nucleation growth theory, this is the theory behind the nanoparticle growth. And okay, you have to consider that when a nanoparticle is formed in a solution, then there is a change in the phase, because you have initially a liquid phase and then you change to a solid phase. So you have to create an interface, and this a curvature at the beginning. The curvature is very high, and then you have to consider that for the formation of the new phase, you have to put energy, to create this interface. Yeah, and this is related with the interface tension. Yeah, so this has to overcome. Yeah, before the formation of the nanoparticle. Yeah. So and below that, formation of these nanoparticle clusters are formed in this very small area. So according to nucleation theory, you have to have at least this critical radius of around 2 nanometers in order to have a stable material. But below, yeah, the nucleation theory predicts that all the things below this around 1 to 2 nanometers are not stable and should dissolve immediately in the system. Yeah, so separate into atoms, and the atoms should be oxidized immediately, so you recover again the silver or the ion that you put at the beginning for the formation. Yeah. But we know that clusters one forms cannot be dissolved, and so we have to change a little the nucleation and growth theory, and putting here that before the formation of this critical nuclei that can grow, yeah, there is the formation of different clusters, and some clusters are more stable than the other ones, and we know that from the gas phase studies that were made in the 80s, that are some cross-shell clusters, means that there are clusters that are more stable than the other ones. The same that in the atomic, the periodic table, you have atoms that are more stable, the noble gases that are more stable than the other ones because they have a cross-shell cluster structure, cross-shell structure. Yeah. So usually in solution, the clusters that are more stable are not the same and in the gas phase, and this is because they can have some ligands and some absorption of species like oxygen or water in the surface, and this change the stability of the cluster. The clusters are very stable. They have activation energies to growth, and at the end to form to fuse and to form the nanomaterial. And this activation energy is around 150 degrees for clusters in solution. But when you support the cluster in a material, they can have at least 400 to 500 degrees Celsius stability. And in some material, like for example in silica, the materials the clusters are so stable in such surfaces that can be stable even until 900 or 1000 degrees Celsius. Yeah. So I told you that the clusters are formed before the formation of the critical nucleus, and this can be this is something that all the people working in nanomaterial before, they just when they just try to follow, for example, the formation of the nanoparticle, always they have an induction period. So there is something at the beginning that you don't see almost nothing. There is no evolving of the nanoparticle, but then suddenly the nanoparticle, for example, you follow the plasmon band of the nanoparticle, then the nanoparticle goes, and you can follow the growth. But this induction period that is always present, so the people understood that as this form of catalytic species B that nobody knew before what it means, but this catalytic species can autocatalyze the reaction. Yeah. So we know now that these catalytic species are clusters, because if you introduce clusters in the solution before the reaction, then this induction period disappears. So this means that the presence of catalytic clusters is essential, yeah, to begin to see the reaction at a particular with time. Yeah. So you can see that during this period, there is a cluster formation, yeah. And this is what we use for the preparation of the synthesis of nanoparticles, just to use a kinetic approach, not a thermodynamic approach, in order that we can form during this time the cluster formation, and thereby changing the parameters, you can focus to one particular size of the cluster. Yeah. And the reason there is one proof of this catalytic cluster that happens before the formation of nucleus, and this is the following. There is a well-known recipe to obtain different shapes of nanoparticles. For example, when you have gold ions and you introduce a reactor in the solution, then you can form these seeds or these nuclei that form after 10 minutes. So when you have these first very small nanoparticles in the system, then you can put more gold and reduction agent, and then you form spherical nanoparticles, very well dispersed because you make the reaction over these sheets, and then the particles are more or less more dispersed. What is interesting is that, and this was discovered by chance, that you introduce in this reaction a very small amount of silver ions. This is 1,000 less than the gold ions. Instead of producing these gold spheres, you produce these nanorods. So the reason for that was not clear, but what we did is just to introduce. First, we just investigate what happens with these silver ions in this media, and we observed that they do not form nanoparticles; they form clusters. So what we did is to introduce, instead of silver, this silver nitrate solution, we made the same but introducing clusters, and we obtained the same. We obtained nanorods. But instead of introducing here millimolar of silver, we introduced nanomolar of clusters. So this means that the silver ion, what they do in the reaction is to form these silver clusters, and these silver clusters catalyze the formation of these particular rods. They are so preferential in one particular plane of the seeds, and then they catalyze in this reaction, and they form these nanorods. Yeah. So, okay, so in order to explain before a little more how this works, then you can say the following. You can plan this following experiment. If you wait 10 minutes to form the seeds, yeah, and instead to use clusters externally prepared, you just make the same reaction, but wait less than 5 minutes. According to our idea, is that you form clusters. Before 10 minutes, you don't have these seeds, you have clusters. Then if you add this reaction at the time below 5 minutes to these seeds, you obtain the same. So this is a proof that you in the system before the formation of it, you have this cluster. Yeah. And, okay, we can use this idea to produce the clusters. And you can see the clusters. Okay, seeing is believing, and you can just make some particular microscopy images because you have to use very soft electrons in order not to fuse the cluster when are deposited. But you can, for example, here to see that this is a mixture of silver 2, silver 3, silver 5, and this large signals here are overlapping clusters. So in this case, you see that mainly you have silver 5 clusters with a small proportion of small clusters. There are other ways to characterize the monodispersity of the samples, and this is, for example, the emission. The emission depends on this gap, and the gap change by changing the size. So if you have only one emission peak like here, you see that it's a very non-dispersed kappa cluster solution, and this is what published before, and you can characterize the cluster, for example, by mass spectroscopy, and you can see that this emission corresponds to clusters of 5 atoms. So, and you can follow, for example, how is the stability of clusters. You can see that these clusters, contrary, is made with material which is easy to oxidize. But these kappa 5 clusters, you can put in nitric acid or sulfuric acid at pH 1 with a very strong basic media like pH 14, and nothing happens. So the clusters are very stable in terms of chemical stability. It's very difficult to oxidize or to reduce the